That advances and that runs it back. Okay. And I can point with that. Okay. This is the crudest PowerPoint I put together in the last 25 years. It took me 2 weeks to put it together, and it was mining information off the internet to answer a question that I had that I got out of the issues dealing with climate change in Alaska. I figure I'm qualified to talk on this topic. I've been educated in enough science and engineering to deal with those issues. I began studying Arctic engineering when I was an undergraduate at the University of Alaska, because I worked in a heat transfer lab under Eb Rice, who's the father of Arctic engineering. And we studied things like heat flow through soils while I was there. So I've been doing this since 1966. From 1979 to 2009, I fabricated over 50,000 temperature monitoring points for soil temperature measurements around Alaska for geotechnical purposes and for foundation stabilization issues. When we put piling in the ground, you can't load the piling until you got freeze back and have add freeze of the soil on the piling that are in there. So I've been interpreting soil temperature data for everybody that I fabricated these devices for over time. So I learned a lot about temperature in the ground. While I was in grad school, I got interested in oceanography because I was working on a project. So I took all the courses. So I am a physical oceanographer also by training, and I spent 8 years in the 1970s actually collecting oceanographic data. So I've done limnology things and stuff. So the things I looked at were that. So I started off with this. I keep hearing Alaska's warming 2 to 4 times faster than the rest of the world. And I've been questioning this for some time. This was from USDA. It says that the USDA Northwest Climate Hub is where I got this from. And there's all these statements about Alaska's at the forefront. Rising temperatures and reduced ice coverage and all that. So that's what this effort was for, was to find out if this is, where do I, okay. I went too far. Anyhow, in order to go through this, I'm going to investigate air temperatures from selected locations around the state, investigate subsurface soil temperatures to determine the status of the permafrost, because everybody's talking about permafrost. And as I indicated earlier, most time people talk about permafrost, they're not talking about permafrost, they're talking about the active layer, the layer that's closer to the surface. And then we've got issues with the receding sea ice. And so the dates that land-fast ice occurs and when the spring break up have a big impact on the coastal communities. And then river and lake ice thickness give an indication of what the weather's been doing. You know, sea ice is rapidly receding, and that may or may not be true. The glaciers are shrinking, and especially the ones that are on the coast that are seawater. And I've been involved with studies at the Columbia Glacier and others. I'd like to see what the studies show for the inland glaciers after the last 2 years of snowfall. We probably have advanced some of the glaciers that we've got. And we got statements that are made all the time about thawing permafrost causes surface erosion and impacts a whole bunch of stuff. So I'm going to start with this. We're going to look at air temperature. This is a map that I picked up from ElDoradoCountyWeather.com. And you'll see that in this blue area, which is the North Slope, the average annual air temperature is 10.1 to 15 degrees Fahrenheit. That average temperature is well below freezing. And down here, this is where continuous permafrost exists. And down here where we have discontinuous permafrost, the range is 25.1 to 32 degrees Fahrenheit. So most of Alaska has average annual air temperatures that are below freezing. And this is fairly recent data. And one of the things that I found is the representation of air temperatures as annual average anomalies are misleading. And this is what I see from blogs and everything that appear on my cell phone almost daily, that the ocean's boiling and that Alaska's melting. One of the things that I recommend is we need to see the actual temperatures in association with these average annual anomalies. Because and I'll get to that in the next video. The average air temperatures, as shown below, are below freezing now and historically. A large change in the temperature is due to the absence of extreme low temperatures. I think I talked to Carol over the telephone about that what I found is not that we're getting warmer, we just have less cold to balance that. So the average, when you do the numbers, looks extreme. And so this is one of the representations we show up here. They've got a plus 6 degree Fahrenheit average annual temperature change compared to historical data. And through much of the rest of Alaska, there's high values. So this is a 12-month temperature curve on the North Slope Burl. And we can see back here in whatever before 1990, there were lots of low temperatures. And we see out here these high temperatures, but they're averages. They're not the actual temperatures. They're the anomalies of the averages. So I got these curves, which are North Slope Burl, and this is for the month of July, which is a warm month. And you can see from 1925 to 2023, the highs, the median, and low value curves look pretty smooth. There's not big increases in temperature in the summertime over that time. And I've got, this is for August, which is similar. There's high temperatures in the past. And then this is January, which the three curves, don't have any great increases in them. And then this one's for February. I would like you to note right here, 2019 was a warm year in Alaska. Nolan and I talked about that. It was a very warm year. But if you look right after 2019, it got cold on the North Slope. And it would, if we were really having serious heat problems, we should demonstrate a fair amount of melting of ice and everything else. So So this was another curve that shows the 10 coldest years and the 10 warmest years. And this is another one that this is based on the annual average anomalies. And this is what gets people, will publish in their things to make their statement that Alaska is warming 2 to 4 times faster than the rest of the world. So the average annual air temperature over much of Alaska is still below freezing. If it wasn't below freezing, the permafrost would definitely be melting. It takes average annual temperatures on the surface to be below freezing in order to provide the environment in which permafrost can exist. Now, the average temperatures have become less cold, so we have more time above freezing, which would allow soils to thaw a little deeper. That will happen. But my take from this, there's much less reason to panic than the media indicates. And that's why I looked at this as, how much do we have to panic about this? I can't read what's underneath your screen sharing. So in the slide that we're back at for February, that 2021, 22, 23, and 24 did show lower temperatures for February after that very warm 2019. So in my opinion, cold comes along often enough to balance whatever warm years we've had. So I don't want to trend the data too soon, because reversals can alter the conclusions. And part of what I saw in my search for information is that people don't really understand what they're looking at when they look at this stuff. I think that the anomalies of the averages is a good sensitive indicator of the changes, but you don't want to base decisions on that. So the following slide, I drew it from my notes from my Arctic engineering course, just to show what the soil measurement and the curves that are represented here are for. This one's for Fairbanks and this one's for Barrow or Uktiavik. The trumpet curve on here for these soil temperature curves is the limit. This is the high limit, and this is a low limit for this particular one. This line here represents the geothermal gradient, and this curve here is a representation of temperature for about mid-November, and it's called the whiplash curve. And as you look at measurements of the temperature throughout the year, it'll extend from out here, and the temperature, the heat propagates into the soil. And I got a note here, the rate of propagation of heat through the soil takes about 6 months to go 30 feet. And it attenuates as it goes through the soil. And there's a point down here at which it's the lower limit of the impact of the surface temperature. The mean annual soil surface temperature for Fairbanks is somewhere slightly below freezing. And in Barrow, it's about minus 10 degrees, or it's somewhere below minus 10, 12 degrees, whatever it is. This is the top of the permafrost in Fairbanks. And the bottom of the permafrost is down here at 35 meters depth. In Barrow, somewhere about a meter deep in the soil is the top of the permafrost, and the zero crossing or the Barrow trumpet curve is about 400 meters deep. In Prudhoe Bay, we have some places the permafrost is 2,000 feet deep. The mean annual soil surface temperature is dependent on insulation from organic matter, the snow depth, and anything else that would provide insulation or lack of insulation of the soil. If the wind blows the soil clear, it'll be colder. If the snow is deep, then it'll be insulated some and it won't get as cold. So there's lots of variation during the year on this, but as long as you understand this. But the active layer is that part between the surface and wherever the top of the permafrost is at. And that's the active layer. So in Fairbanks, it's about 5 meters deep. On the slope, it's a meter or less. So I just restate what I had in there. So the people who lived out in the middle of nowhere would dig down to store stuff either in the summertime or the wintertime. In the summertime, you can dig a hole in the ground, 6 feet deep, and you can keep your food cool, keep your meat cool in the summertime if you don't have ice. I was telling Nolan that I had a data logger that was installed 100 miles offshore in the Beaufort Sea, and they buried it 3 feet in the snow and ice pack to keep the data logger warm. And it stayed out there all winter until March. So we bury stuff to keep it warm, and in the wintertime where we bury it to make it warm. So, and if we have an increasing active layer depth, that would indicate the permafrost layer is decreasing, that it's been impacted, and that would be if the mean annual surface soil temperature is increasing in temperature. Where you at? So this is a curve that I got from, I had trouble finding soil temperature data online, but I found this from Red Dog Mine permafrost studies. And in this, the top of these curves is about 8 meters. So there's no active layer data in here. And they have it's a 10-year history from 1986 to 1996. And so I just extracted the data from 1 year. So this is a value in the summertime, and this is a value in the wintertime. And you can see that the curves come together here somewhere, and that's the extent of the variation from the surface. And this is the geothermal gradient that is fairly constant. And this is the data that I extracted out of the set. So one curve was for 15 December 96, one's from the 15th of April 98. So, but it's just so you can see what the curves look like. And down at depth, it's above freezing when you get below 125 meters at Red Dog. Red Dog is north of Kotzebue It's the zinc mine over there. So as I said earlier, the top of the curve is at 8 meters depth. And one of the things they found, anything that said permafrost on it, they had absolutely no active layer data in it, which I'm not seeing it before. All of the temperature strings that I fabricated had more dense sensors near the top so that you could see what the active layer is doing, and they would be deep enough to get down at least into the permafrost far enough. A lot of them were used to determine foundation pile design. So you get piling deep enough into the permafrost. And then one of the things you use the temperature probes for is to measure for freeze back, because you can't load piling until you've got freeze back, and the add freeze is holding the piling in place. So one of the records I found did have permafrost temperatures in Alaska that do show a warming trend on some of them. This set here doesn't show much change, and it's from the interior of Alaska, which is less affected by the changes that we've had. And these are from up in the North Slope borough. These are points along the pipeline or around Dead Horse, Cattobic, and Barrow, or on the coast. West Docks on the coast. That's where the seawater treatment plant's at. The rest of these are down in the Brooks Range, and they do show more warming in the 1980s and in 2020, but these values are all still well below freezing. The permafrost here is not melting. It's just warming. It's not melting. So foundation pile that are set to depths well below the active layer would support surface structures. And I've been involved in the installation of all kinds of projects in the North Slope that are pile foundations that we've been designing them for the last, I've been involved with them for the last 30 years or so. And there is, in recent years, we do drill deeper for the installation so that it can accommodate a decrease in the thickness of the permafrost layer. I looked at lake and river ice thickness just to see what kind of records we had. So this was a record in Barrow of some lakes there, and these are the lakes. And you can see that in more recent years, up till before 2019, they did show a significant decrease during the years that were a little warmer than in the past. But what I've heard about the weather on the North Slope this last winter, I think it's been described as brutal. So I expect the ice thickness that they'll have for 2024 is going to be quite a bit thicker than this. So the ice is thicker in colder winters. Snow cover will reduce ice thickness at any temperature because it's insulated. So snow depth is part of the record keeping that they need to do on ice temperature. Now this, I don't know if you've heard of the Nenana Ice Classic. They've been since 1917. They've been putting a tripod on the Tanana River ice at Nenana and bet money on when it's going to go out. And this record that they found, they did a trend on this at this year. In 2024, on the 4th of May, the ice still hasn't gone out. So this is kind of defying the trend. The ice was as much as 50 inches thick this winter on the Tanana River. So the trend is a little premature. So I've got these records as of May the 4th. The ice has not yet gone out. And you can see that the ice has been up to 50 inches thick earlier. In 2023, the ice went out, on April 21st, which is not real early, but wasn't near as thick. In 2013, the ice was 50 inches thick, and it went out on May the 6th. So when people try analyzing the data before they got it fully understood, they're trying to make a point, and they start trending too soon, I think you're going to end up making wrong decisions about what to do. You need to understand what's going on. So, so this is one of my takeaways. The trends that I've seen online, I've been trying to get them probably mostly for shock value or to scare people into reacting to climate change more rapidly. But in Alaska, we can't afford to overreact on things. We need to deal with the facts as they are, with the data that's there, and make our decisions that way. I've been dealing with engineering issues in cold climates for too much of my life. The other one about the Arctic sea ice is extent is decreasing, and I've been tracking this for a number of years, and it is not decreasing annually. It's not decreased in a number of years, and this red line here is the average ice edge from March 1991 to 2020, and there's ice edge down here. We got good shore fast ice on most of the coast of Alaska that does get ice. This is another anomaly picture, and they've got colors in here, and like I said, I've been looking at this type of data for years, just tracking is the sea ice really less. I was going to have another picture. Okay, so it's not decreasing every year, but we need to continually monitor this. And I once found a chart of the time of land fast ice each fall for a number of communities, and then when the ice broke up in the spring. These are records that probably need to be doing, especially for communities that Amy's been working in with AVAC, where coastal erosion is an issue. They need to be tracking that. I've been tracking they put a record of multi-year ice along with new ice, and the multi-year ice is increasing. When I worked at the Institute of Marine Science in the 70s, we did have projects on Ice Island T3, which was an iceberg that got caught in the ice flow years and years and years earlier. And so they had a station there that was manned. They'd fly people out in Hercs and spend time on this isolated thing that was moving around, and it finally broke out of the ice pack. So I look at it and say it could be our Arctic sea ice is making a comeback. I don't know. I just keep track on it. But these are things that we need to actually have a monitoring of, and I think to make it more available to the general populace in Alaska, so people who have to make decisions have got real data on these things and not the scare tactic media releases that are out there. So my conclusion is Alaska's not really warming 2 to 4 times faster than the rest of the world. We have warmed up over time because our growing season's extended. But anybody who lives here, living here feels pretty much the same as it did 80 years ago. There is some warming of the permafrost, but it's not melting like people are saying. And it only takes 2 or 3 cold winters to reverse the trend. And the soil temperatures should be presented in their own values. One of the things that I found in the data that's presented online, there's lots of research projects for how's the melting of the permafrost going to affect the release of CO2 and methane into the atmosphere. It clouds the permafrost stuff, in favor of the CO2 release. But the important thing is knowing what the temperatures in the soil are. I said that relative temperatures are a good sensitive tracker of changes. But my interest is we have to do things right. So we need right information, not fabricated information. Okay?
Yeah.
I can be done, I think.
Thank you very much, Bob. I think you gave us a really good lecture on looking at the data, what it actually means.
Yes.
And actually looking very seriously at what we have to measure. Like if we want information about something, what is it that we can measure to get that information? And that has been for researchers and others has been a question for the ages, really. Like because we have a tendency to measure what is easily measured.
What's convenient.
Well, you know, sometimes
not necessarily meaningful.
No, yeah.
So I just have a question on the actual temperature measurement. When you measure, so if you go to an area, do you go into the active layer? Do you measure on top? How do you actually measure the temperature?
They drill holes in the ground.
Oh, so it's a specific depth and you measure?
To a specific depth, and they'll put down a PVC pipe. It's not, not much bigger than the string that you're going to put in it.
Okay.
We've generally been filling them with propylene glycol because it's an environmentally
neutral,
acceptable liquid. And then put the temperature string in there and kind of seal it off so that whatever your top measurement is a measurement of in the soil. If we need an air temperature measurement out of that, we generally bring a probe out to do that. But I fabricated them out of thermistors and telephone cable. I do it.
Oh, that's good. I wasn't sure.
Yeah.
You had me thinking when you said, that the temperature changes based on the insulation layer.
Which is a different sensor. They've got a different data logger that can transmit.
Yeah, so I have the next question. So I'm questioning whether ground temperature is a one-to-one correlation with permafrost melting evidence. Because from the studies I've seen of people studying the melting of the permafrost, what they have said is that the ice content of the permafrost plays a role into whether or not it will melt, and that rain events are extremely powerful in initiating melting of the permafrost.
What kind of events?
Rain, as opposed to temperature per se.
Yeah.
So
you're talking about active layer and not permafrost.
No, permafrost. So
the permafrost is too deep to be affected by wind.
Okay, or the portion of the ground that causes measurable changes that people are observing. So
That's-
whether it's purely active layer or permafrost or both, I don't know. But what they're referring to is the changes they're seeing from the air and the
Yeah.
the collapse of cliffs, the collapse of riverbanks,
Okay.
all of these things. And they're saying that it's due to rain and and that these areas that have higher ice content in the ground vulnerable to those melting events. So I'm wondering what your thoughts are. Are we measuring the problem completely when we're looking at ground temperature, or are there other variables that we should be
When you talk
measuring?
about ground temperature, you're just talking about surface temperature. You have to measure to some depth
Yeah,
in
all the
order to
data
get
you showed.
meaningful information.
Yeah.
And if you're looking at something that's got a surface phenomenon, you're probably looking at things that are happening in the active layer.
Mhm.
If the active layer has a high moisture content, it will have ice.
Mhm.
And when you've got ice and when you got moisture in the active layer, that's when you're getting more ground movement as the ground freezes and cools. And that's where you get the frost jacking. It's where buildings go up and down. Or if you just set anything on the ground surface and you've got high moisture content, like some of the pictures that were shown of villages, the ground's going to expand and contract as it freezes and cools. And when it gets, when it settles back down in the summertime, it'll be uneven in a different way than it was uneven last year. So you get ground shifting. If you've got, depending on your soil type, that's when the high rain, or if you've got flooding, will, just change a whole lot of stuff because it's not normal. We got wet areas that don't really get a lot of rain. Most of the Arctic is considered a desert. Caribou are a desert animal. And that's why I try to correct people on things that the part that's most affected is going to be the active layer, that's where the warming is going to be. And that's why you need to have a continuous set of measurements that go down into where the permafrost is at. So your data is anchored in something.
So I think one of the things, if you look at popular literature, like newspaper articles and so on, that people actually confuse the active layer with permafrost.
Yes.
They call it areas of permafrost, but they mean the active layer.
Well,
So,
it's frozen ground,
Yeah.
but it's not permanently
Right.
frozen.
yes.
The part that
Yeah.
they're looking at.
So the language is used inaccurately.
That was the whole point of my doing
Yes.
this. And
Yeah.
we had some presentations on remote monitoring.
Yes.
I know that a lot of the people involved in remote monitoring made mention in their things that they'd rather do that than get ground truth data because it's too labor intensive. But you have to have ground truth, whatever you're doing, especially if you're trying to do subsurface for sea temperature or salinity or whatever it is. You've got to have measurements from within the water, the ground that's there, so that you have something to better evaluate the data that you're getting from
And you have
the
to,
remote sensing.
you have to calibrate it, right?
Well, not just calibrate, but you got to compare.
Yes.
You have to do a comparison to what's theirs.
Yeah.
What did you see here this summer? So when we fly over and we've got a record, we see these anomalies. What do they represent?
I understand.
And
I had an idea, but it's a little bit tongue in cheek, okay? Because we just heard about all these uncapped wells, so maybe some of them could be used to measure temperature.
No, but they've got
I am tongue in cheek.
they have steel casings, and so they
That's
would
true.
affect the measurement of the temperature. That's why we use. And
I know you're
for-
right.
for the coastal areas where there's river banks and coastal stuff, when they call that Permafrost, it's not. If it's exposed from three sides or whatever it is to summer temperatures, it's not permafrost. And when you look at the communities where those are at, there's lots of lakes or rivers or oceans nearby. Underneath all of the bodies of water, there are thaw bulbs that extend underneath the land. And where there's a large lake in the Arctic, there will be no permafrost at all beneath it,
Mhm.
because it creates a thaw bulb and it's too big for the permafrost to extend
To
underneath
penetrate.
it. So most of those things that people are calling permafrost, and I looked at one of the photos, the ice wedge that was in there was only about that thick. So it was not a multi-year ice wedge. It had come from probably last winter's freezing as the water soaked into the ground, into the pattern ground.
Okay. Was there another? Yeah, I did see questions. I wasn't all wrong. But I noticed you all gave me a laughter when I did my tongue in cheek.
Oh,
You were okay.
oh yeah, I try to pay attention. So, I think just kind of this point here, if you look in some places in Alaska, you're getting a lot of erosion. You see a lot of glacial silt. I was talking to Carol about this yesterday when she's in the car. We're head over to the EIB building at UAF, and I mean, I grew up in Bristol Bay. Erosion was a chronic problem out there. You know, long before I was alive, long before our parents were alive, the communities had to move whenever stuff fell off the edge of banks. There's old houses that are built on the edges of bluffs that are falling off the edge right now. And they were probably built 65 or 70 years ago. So, and if you fly over that region, you can see places where creeks and rivers have rerouted themselves spontaneously. So, hard to say when the process started.
But none of those areas, Dillingham, I don't think is really a permafrost area. It's at the bottom of the discontinuous permafrost area. But
Yeah.
but we've had houses fall into the Matanuska River. Yes, there's lots of rivers that people have built on the edge of, and the river changes course. And you fly over the Kuskokwim River, it's changed courses. You got all kinds of horseshoe lakes and horseshoe patterns in there. So if you build anywhere, anybody's at risk, and you have to, when they built those, 100 years ago or 60 years ago, they didn't do temperature studies under there or do a geotechnical, find out how load bearing, or if there was anything under there to support. So if they built it on sand, it's going to collapse. So bedrock's still a thing to look for, and people often did, but the riverbanks and the coastal areas, we need to adapt. You can't save the river from moving.
Hey, Bob, impressive work. Congratulations. Do you actually maintain consistency? Do you measure the same spot?
What's that again?
When you measure temperature for permafrost, for instance, do you measure the same spot?
When they bore a hole in the ground and
Yeah.
put a pipe in there and put string down, it stays there.
And so the next year you come back and measure it, maybe.
Or throughout the year, it depends on what kind of record you're trying to do. Normally, you want to get a record throughout the year to see how it's behaving.
This is a perfect set of data you could put on Dataport.
Yeah, but yeah, I think one of my recommendations is, I think the state of Alaska needs to, foster having a database of stuff, so that when Amy's working in some village, she's got a record to go look at and say, what do I have here? Because I don't know, some of the villages probably don't have the soil temperature. Go ahead.
So when some of the early wind turbines were put in, there were temperature monitors installed for that. However, the technology is a little bit like, we can't talk to any of them anymore. At least
Okay,
not
what do you-
right now. The temperature sensors that we had installed previously, right now we can't read them. And so I think being able to maintain just the idea of communications and,
Yeah.
you know, getting all the data and having like, that's why I'm really excited
Yeah.
about IoT
Yeah.
and all that.
The temperature probes that I fabricated prior to 2009, if they're still in the ground, but they don't have a connector on them anymore, I probably still have the means to change the
Yeah.
connector on them. Because beaded stream's a totally different thing than what I fabricated,
Right.
but, and, I don't know how.
Yeah, we'll work on that.
I
My
can help you
comment
with
is
that. If you
different.
got something, I can tell you.
So my comment is I realized I forgot to bring up thermosiphons, which is something that I think is important to this conversation.
You talking about the Arctic Foundation's thermosiphon?
Yes. Yeah. So if anyone's unfamiliar, you know, you drill a pile into the ground, but then you have what's called a thermosiphon that basically has like a refrigerant in it that at the top there's a bunch of essentially cooling fins.
There's a radiator
Yeah.
at the top.
Yes. So what it effectively does is the heated chemical rises up
Yeah.
and then gets cooled by the radiator, and
The
it
heat does a
pulls the
phase
heat.
change on the gas that's in the ground, and it comes up and hits the radiator, and then it turns into a gas, and then it's the heat's taken out of it, and it turns liquid and falls back to the bottom of the tube.
Right.
And the temperature that it will cool to is based on the gas type and the pressure that's maintained within the thermosiphon.
Yes. I don't actually know the specifics of how they work. I just know that they essentially act as like a passive
Yeah.
cooling system.
And they're very effective, and they work, and I've been working with Arctic Foundations with temperature probes to monitor their stuff, because you need to have freeze back before you load the pile or whatever it is the thermosiphon is protecting. The
Right.
thermosiphons have been used to stabilize the riverbank in Bethel so that the airport would not erode. They put that in 20, 30 years ago.
Right. We put them in for our power plant upgrades
Yeah.
in Bethel. We put them in for the wind turbine in Stebbins. So now you have that passive cooling
Right.
effect. But I think one important question where we still have to do the monitoring and the temperature measurements, like you're saying, you know, if our permafrost is warming, you know, even if you have thermosiphons, how do you know the thermosiphons are still working? You know, and so I think that's a question that we can't answer now, and it's at least we have a good measure with those
Yeah.
devices. But
Then what Ed Yarmack does, he does pressure measurement on the thermosiphon, and he can tell you what the temperature is in the ground that it's maintaining.
yeah.
Okay, sure, and you're between us and coffee or snacks?
I'll give a quick answer.
Nice snacks.
So, you know, down in the lower 48, the thing that I always hear about every couple of years is, you know, what's going on the Yukon River. That's the one that's always watched. And the question I have is and I don't know how to technically answer, but maybe you do. Is there any correlation to the temperature measurements you measure and the amount of ice flow in the rivers and the erosion? Is there use
the
that as a
colder
data
the
point?
winter, the thicker the ice. And in 2023, they had ice jams on the Yukon River. One account I just read in the paper was from somebody who did a canoe trip down the Yukon River and went past 40 Mile that was wiped off the bank
Mhm.
by the ice. And I was telling him, back in the old days, we used to use dynamite, or or on occasion they've used fighters to drop bombs on ice in the Yukon River to break it up if it was remote from places that it was hard to get dynamite out to where the ice was big. But ice jams are a big problem in rivers in Alaska. They have problems with ice jams on the Kuskokwim River, the Yukon River.
But there's no real correlation to the thermal measurements that you make.
Well, they would, I mean, if your thermal measurements from the shore show it was cold, the ice is probably thick. if it's cold, and if you look at some of this, if it warms up early, like if it starts warming the end of February, the ice will melt. And then when the ice goes out, it's not as thick as it was, but it looks like a Nenana this year. It would get cold again after it lost some of its thickness. So it was 50 inches thick in March, and it got down to something less than that, and then it got cold again, and it went back up to 50 inches thick. So it depends on, it depends on subjective information. What was the
Like you have ice dams here, like I've seen them in Ottawa, and they were considering using dynamiting an ice dam there because the water behind it was going higher and
Yeah.
higher and higher and was a flooding threat. Okay,
And so
so you
flooding's one of the
It
problems.
can happen everywhere.
Flooding's part of the problem behind an ice jam,
Yeah.
but the rest of it is the water pushes the ice jam along.
Yeah.
It can wipe stuff off the
Yeah.
river bank. It'll go way up on
Yeah.
the bank, and it's just like a dozer
Mhm.
running down the bank. And so if there's any structures in the way, they're gonna be gone. Whether it's just trees and moose or whatever it is, it's
Then you call it a natural effect.
they're all natural events.
That's right. Well, thank you very much.